about doing Python with unstructured meshes.
Cool. Thanks for bearing with me. My name's Florian. I work with a bunch of people at Imperial College London on a tool called PyOP2, which is a framework for performance portable unstructured mesh-based simulations. And specifically, I'm going to talk about its application to finite-element computations. So let's look at what does PyOP2 look like from a SciPy perspective. So those of you that are computational scientists, and probably many of you who aren't, will agree that SciPy is a lot about producing high-level interfaces to numerical computing, and PyOP2 is one such interface for unstructured mesh-based computations. And it allows you to efficiently execute a kernel over an unstructured mesh. And layered on top of that, we have another tool called FireDrake, which is a performance-portable finite-element computation framework, which is driven by PyOP2. And it allows you to drive finite-element computation from a very high-level problem specification. So that's the high-level view. But below that, to run efficiently, we need efficient low-level operations. And a key aspect of our framework is that we separate the low-level implementation from the high-level problem specification. And that is due to the paradigm shift that computational science has experienced with the advent of many and multi-core hardware. So what we do is we generate platform-specific implementations from a common source instead of hand-coding them. And that opens up the space for performance portability and compiler-driven optimizations. So I'm assuming that maybe not everyone is familiar with the finite-element method, so this is a very high-level overview. So you have a partial differential equation, and you express it in its weak form, as you see for the Helmholtz equation up here. And to do anything with it, you assemble a linear system of equations, which you then solve with a standard. So you get a sparse matrix, which you solve with a linear solver. And the thing to realize is that this is a perfect fit for the model that we propose or that we implement, because normally you solve PDEs or you solve finite-element methods on unstructured grids, and the local assembly operation, so this numerical integration of this weak form of the PDE, is done for every element of the mesh. So this is the numerical kernel that you can execute in parallel over the mesh. And this is what we do using PyOP2. And so how do you get this kernel? The great thing is that the finite-element method is very well defined in mathematical terms and is very well structured. But it's also very complicated. So writing these kernels by hand would be very tedious. But happily, we have a means to avoid that. So there is a domain-specific language for finite-element computations called the Unified Form Language from the FEniCS project. And it allows you to express this weak form of the PDE in a near mathematical notation. So if you compare the PDE that we just saw, and this is literally all the Python code that you would write in UFL to define this model problem. So you define a finite element and finite element spaces on there, and you express your PDE. So the FEniCS project not only comes with this domain-specific language, but it also comes with a form compiler called the FEniCS Form Compiler, FFC, and it takes this UFL expression and it generates the kernel that we're after. So we've slightly adapted FFC to our needs, and what we basically get is when we pass this UFL expression to FFC, we get a kernel that looks a bit like this. So this is actual generated code, but I've stripped out some parts for clarity. So how do the pieces fit together in PyOP2? So the user writes their code against the PyOP2 API. And what they need to provide is a kernel, like the one we just saw. They need to provide data, and they provide access descriptors, which is how these kernels are accessed. So how the data inside the kernel is accessed. And this is then executed by the PyOP2 runtime core, which takes care of partitioning and parallel scheduling and the parallel execution of the kernel over your input data. And all the linear algebra operations, we defer to linear algebra libraries like PETSI and CUSP. And the great thing that we get is we support different hardware backends, and this is completely abstracted from the user. So the user writes their code once, but they can run on a multi-core CPU, they can run on a GPU, they can run distributed parallel with MPI, all without changing the source. So we take care of all the magic sort of under the hood. So how does this look like? One thing that PyOP2 does is it partitions your mesh so that the mesh partitions fit in the local cache memory of your device. So that's the shared memory on a GPU or the on-chip cache on a CPU. And it stages this data. So in this diagram, we see the partition mesh with 3 partitions. And we have a set of nodes, and we have a set of edges connecting those nodes. And say we want to run a computation on the edges, but the data is defined on the nodes, as is normally the case in the finite-element computation. So you have a certain physical quantity which is defined at every node. So you need to pull in the data at the nodes, but you run your computation over the edges. So PyOP2 schedules that parallel computation over all the edges in the mesh, and it does this partitioning, and it stages, so it loads the data at the vertices. So the issue is now that we have a number of edges which access the same node. And when we run this in parallel, then we get race conditions. So when multiple threads want to update the same value in parallel at the same time. So what PyOP2 also does is it colors these partitions so that no two colors share the same node. So as you can see down here, I've highlighted the blue colored edges, and as you can see, these edges, every edge touches 2 vertices which are staged in shared memory, and no 2 blue edges touch the same node. So this data is then staged so that in the center you see the nodal data for the blue partition, and we can load this contiguously from memory, which is important for memory access on modern architectures, in particular on GPUs. But we also have a few non-contiguous accesses from the nodes that span the partition boundaries. So we try to minimize those. So PyOP2 can schedule these partitions to run in parallel, and within the partition it will schedule each color to all the colors to run in parallel so that we get the maximum level of parallelism that we can get for that particular problem. And this operation is tuned to whichever architecture that you run on. So this will look differently on the GPU than it does on the CPU, and it's all taken care of for you. So this is then how the entire toolchain looks like. We've already seen UFL, which you use to to specify a finite element problem, which is then passed to FFC. And FFC provides the kernel that we run for a parallel computation of a finite element problem. But we also need the data. And we, instead of re-implementing all that functionality, we wrap a library called Fluidity, which is a CFD code, a traditional CFD code, which has a Python interface to its data structures, which we've extended. So this is where we get the data from. And this comes together at the PyOP2 layer. And PyOP2 takes care of everything from that point and schedules the parallel computation, as I've just described. So what this delivers also is a separation of concerns. So we allow scientists of different domains to work at their level of expertise. So we have 2 points where domain specialists interface that develop mathematical models and solve physically based problems. So for those that work with finite element methods, they can sit on top of Firedrake and specify their problems in UFL. But those that have problems to solve that don't fit the finite element model, but that are still unstructured, they can write their kernels by hand or use some other means to get a kernel, and they can work directly at the PyOP2 layer. And of course, there is room for people to contribute to either of these layers. So numerical analysts might work on finite element methods and contribute to FFC, UFL, Fluidity, and parallel programming specialists, they might contribute to PyOP2 and implement support for a new hardware platform like the CUDA. So how do you drive finite element computations in Firedrake? For those who are familiar with FEniCS and the FEniCS finite element package Dolphin, this will look familiar to you, which is intentional. So we try to stick as closely as we can to the Dolphin interface to make it easy for people to switch or to use a framework. So what you do is you read in a mesh file, and you define a finite element function space on this mesh, and you define what element you want. And this is all the element types that are supported by UFL and FFC. And then we see the same problem specification that we saw before for this Helmholtz problem. And when you've defined your finite element forms, you just pass them to a solve method, and this under the hood will call PyOP2 for the parallel computation, assemble the matrix and the right-hand side as I showed you earlier, and then finally solve the linear system using a sparse matrix solver on that platform, for instance, PETSI or CUSP. And this is all completely abstracted from the user. And as I said, you can also use PyOP2 for non-finite element computations. So this is an example how you might write a kernel by hand, which does the normalization of a vector field. So the kernel signature is very simple in this case. And below here you see the parallel loop call. And you pass in 3 arguments. The first one is the kernel that you want to compute. The second is the set that you want to compute on. So in this case, we want to compute on the set of nodes. So this computation will run, the kernel will be called for every node of your mesh. And then you pass in data with the access descriptor, which consists of the mapping that you want to use. So in this case, the computation in the kernel is done on the nodes themselves. So there is no indirection. So this is then a direct mapping or an identity mapping, which we call it in our API. And since you since you both read the nodal values and you write them, the mode is read-write. And so this mode is important for the scheduling, because when you never read values, we don't need to stage them in for reading, and if you don't write them, we don't need to stage them out after they've been computed. That's why we need to know. And so to finish, I'm just going to show you a few performance comparisons with the other frameworks that I've showed you. So this is a finite-element and advection diffusion problem that's running for 100 time steps. And on the x-axis, you see the mesh size. And I'm showing you the relative speed up over the Fluidity CFD library, which we compare against. So that's a traditional CFD code written in Fortran. And this is a sequential run now. So Dolphin is about 2 times faster because it's implemented a little bit more efficiently. But Dolphin is still a traditional library, which you interface from Python. And we run about 4 times faster because we have less overhead, because we can, this code generation and the scheduling is all happening at runtime. So we can tune to the specific problem that you're solving. So when we run MPI parallel, this is what we get. So I've left in the previous graphs, but so this time Fluidity scaling is actually pretty good. So we get around a factor of 8 on 12 nodes over the sequential baseline, and Dolphin we get about speed about 15, and we're a bit between 15 and 20. And when we run on a single GPU, which is not supported by either Dolphin or Fluidity, we are even slightly better for larger meshes. So this is running on a single Tesla C2050. So we get about 20 times speed up. And so a single GPU gives us about the performance of one socket, of one node, 2 socket node, approximately. Right. With that, I'd like to thank you. And these are some pointers to the code. And the slides are also online. So I'm actually running the slides off GitHub. So feel free to have a look around. And I'm happy to answer any questions.
Mm-hmm. But you're only about a factor of 4 over your own code in serial, whereas they got about a factor of 8 from serial to parallel. Do you have any insight into what the difference might be?
Yeah.
In serial, you were already 4 times as fast as they were, and then you go another 4 times as fast when you go to 12 nodes, whereas they went 8 times as fast by going to 12 nodes. So there's a scaling. You clearly get a better performance, but you don't get as good a scale.
Yeah, so the reason is that there's a bit more overhead we have for parallel computations, because we run a completely different code path. So the question was why so the speed up that we see with 12 MPI nodes, why we only get about a factor of 4 to 5 over our sequential, whereas Fluidity get about a factor of 8. And so the reason is that we run a different code path when we run with MPI. So what we do is we need to exchange halos between the petitions, and we can completely strip out this computation when we run sequentially, which gives us, so we get a much much more efficient sequential execution path.
You're using the same partitioning that Fluidity is using?
That's right, yeah. So we, in fact, use Fluidity's partitioning, which is the main reason that we actually interface to it. So the, writing an interface to a mesh is not that hard, but actually doing the partitioning and the halos and what data you need to exchange, that's the hard thing.
What solver are you using?
This is using PETC, PETC-CG. Yeah.
I was curious about the non-finite-element kernels. It looked like it was sort of a shader language. Is that something specific to PyOP2, or does it depend on what platform it's being run on?
Okay, so the question is about PyOP2 kernels, so how you specify them, because so this example looks a little bit like a shader language, and whether they are specific to the platform you run on. And so this is basically just a string, a C string with, so this is just a C code as a Python string, which you just pass to PyOP2. So this is not dependent on the platform. So we take care of the necessary annotations that you need to do when you want to run on a GPU. So one thing we want to look at is actually that you just write a Python function, and that we then just compile that function. So using LLVM or something. So that's part of future work. Yeah.
Have you done anything with like multi-GPU, like MPI over a different GPU?
Not yet. This is one of the things that we're actually currently working on. Hopefully we have that running pretty soon. The problem is that it's not as easy to find a linear solver that, we can't just take an off-the-shelf linear solver that does a multi-GPU because it doesn't exist yet.
Okay, with that, we'll wrap this up.
Thank you very much.